at the key turning point in my mathematical life. I was a third-year graduate student at Harvard. I had no thesis and no thesis advisor. But I had been working with Dennis Sullivan for 2 years, although he didn't know it. I got some notes that were Xeroxes of Xeroxes of Xeroxes from Bill Goldman, and I just thought they were amazing. They were called Conformal Dynamical Systems. And so I started a seminar on these notes. The only people who came were Dave Wright and Bob Devaney. And I gave all the lectures, and I stayed up many Friday nights trying to figure out what was going on in these amazing notes. And then Dennis kindly agreed to take me on as a graduate student. And in the middle of my 4th year, I had an advisor, but no thesis. And I was at IGS, and it was almost Christmas. And I finished my thesis, and I went and told Dennis at lunch, and he said, well, I guess you can graduate. And so that's only one of many tremendous positive influences Dennis has had on me. One could also say I spent 2 years of my life trying to add a few entries to a dictionary.
Yeah, but it's a one-page dictionary.
One-page dictionary. It took me 400 pages to elaborate the entries. And of course, that's just that dictionary is just one small part of Dennis's contributions to mathematics. So happy birthday, Dennis. And it's I owe a lot of where I am now to your influence and help. So I'm going to give a colloquium talk, if that's okay. After hearing all the reminiscences about Dennis's amazing talks, I'm glad I'm not giving a Blackboard talk. Although I have a Blackboard here with me, just in case. And so it will pale by comparison to a Sullivan talk. But let me give it anyway. So I have slides. Let me share them. Okay, so you should be able to see the title, which is Billiards and the Arithmetic of Non-Arithmetic Groups. I like this title because you have to pronounce the word arithmetic in 2 different ways in the title. And the discussion I'm going to present is a pretty long arc. And so I'm not going to be able to touch in detail on certain aspects of it, but it owes a lot to all of the people on this list. There's some heights built into this, going back to Day, Manning, and Birch. There's some work of Leutbecker and Veitch, Maser, Forney, Miller, and Leininger, and Hubert, and Leno, and Davis, and Liliev, mostly on billiards and dynamics over moduli spaces. So this will be a talk that combines dynamics and also some arithmetic and algebraic geometry. And my goal is really to sketch how these different disciplines are interrelated through really 1 or 2 specific examples. Okay, so I'm going to start by talking about triangle groups. So, but let me first state a theorem, and I'm going to try to illuminate this theorem through the specific example of triangle groups. So the theorem is going to involve a lot of words I can't elaborate in detail, but I want to state it. Actually, it took me maybe 2 or 3 years to come up with the statement of this theorem. And this is, again, something that Dennis often told me. I'd look at his paper, I say, well, what do you work on when you work on this paper? He says, I mostly work on the statements of the theorems, which blew my mind because I thought the proofs were what it was all about. But getting the right statement can be a breakthrough in its own right. That's something I learned from Dennis. So here's the statement. It has to do with a real quadratic field. So like Q adjoining the square root of a positive integer. Associated to that, there's a surface called a Hilbert modular surface. It's a lot like the upper half plane modulo SL2Z, but it's built out of 2 copies of the upper half plane and the ring of integers in this field. And we suppose that we have a certain kind of curve, by which I mean algebraic curve, immersed on this surface, and it's geodesic for a suitable metric. And then the theorem is that either this curve is a Shimura curve, which is a kind of curve that people have studied for generations now, or this curve has cusps, and its cusps, whatever that means, coincide with the projective line over K. And there's some sort of height associated to this each cusp, measuring how complex it is. And there's a quadratic height bound on the complexity of each cusp. So I'm going to illustrate this through specific examples. I just want to.
Does geodesic here mean totally geodesic?
No, it means it depends on what metric you think. So when you ask that question, you're implicitly assuming a metric. And the metric I'm taking here is the Kobayashi metric, which is not a Riemannian metric. So geodesic means that V is covered by the graph of a holomorphic map from H to H. It does not mean it's something like the graph of a Mobius transformation from H to H. So it's not geodesic for the Riemannian metric, it's geodesic for the Kobayashi metric. If it were geodesic for the Riemannian metric, it would be a Shimura curve. So I'm studying a broader class of curves that include Shimura curves, and it's sort of like the difference between the Bay-Peterson metric and the Teichmuller metric. Okay, but let me amplify this with examples. Oh, and I will try to say, this might be everything I have time to say about the proof. The proof is by a new kind of descent argument that uses a height that's built out of a mixture of Hodge theory and arithmetic. So let me bring this down to earth. So what is a triangle group? It's a certain specific lattice in SL2R, discrete group of 2 by 2 matrices, and it uniformizes a Riemann surface that's uniquely determined by these 3 integers p, q, and infinity. In fact, it's a hyperbolic surface. It's topologically a sphere with 3 special points. The 2 of the points are orbifold points. They have cone angles of pi over p and pi over q, and the 3rd point is a cusp. That's the quotient of the upper half plane. So it's uniquely determined by these integers p, q, and infinity. And in fact, if you try to write down the group, the traces of the elements you get won't be rational, because you have to take things like p and qth roots of unity, or at least their sines and cosines, to form these group elements. So it has an associated field. And the field is known exactly. It's generated by various cosines and their products. Okay, so this is the domain of groups I want to inspect today. And these groups are of 2 types. Sometimes they're arithmetic, and sometimes they're not arithmetic. So it turns out they're arithmetic exactly when the trace field is Q. So when the trace field becomes quadratic or cubic, which is the case for almost all P and Q, as its degree over Q goes to infinity, it becomes non-arithmetic, and in some sense even less arithmetic as P and Q increase. So let me introduce you to some of these triangle groups, or maybe reintroduce you. So here's one that you already know. This is the arithmetic case. It's our old friend SL2Z. This is nothing more than the 2-3 infinity triangle group. It's the group of 2 by 2 matrices, determinant 1 with integer entries. And it gives a tessellation of the upper half plane that we're all familiar with. There's a fundamental domain, or half a fundamental domain, for the group action drawn here. And you can see there's a 2-3 infinity triangle in the fundamental domain. You take 2 copies of that and glue them together, and you get the 2-3 infinity orbifold. That's how this group yields the 2-3 infinity orbifold as a quotient. And its generators are very simple. It's generated by z goes to z plus 1, and z goes to minus 1 over z. Z goes to z plus 1 glues these 2 vertical edges together. Z goes to minus 1 over z. That fixes I. It fixes the 2 point here, and it glues this red edge to the adjacent edge in this standard fundamental domain. Okay, now I say that this group is arithmetic, and the reason it's arithmetic is it has this super simple description. It's just SL2Z. So you just find the integer matrices that satisfies some simple determinant equation, and those are the matrices you get. Oh, and by the way, this, as you can see, the fundamental domain is not compact. the orbit of the place where it touches infinity, those are called the cusps of the group. They correspond to this infinity here. And as is well known for SL2Z, there's this invariant packing by circles called the Ferry packing. It's invariant under the action of SL2Z. And the places where these circles touch the real axis are exactly the rational numbers plus the point at infinity. Those are the cusps of SL2Z. So let me sum up the great features of the arithmetic case. Here's this group. I told you what its generators are, but I can tell you much more. If you ask me what numbers occur as matrix entries, the answer is every integer. If you ask me when can two integers be a column of a matrix in SL2Z, it's a pretty simple condition. It's that the two numbers are relatively prime. Their GCD should be 1. You ask me what the cusps are of this group, immediate simple answer, they're the rational numbers plus infinity. So an arithmetic group has the property that you can inspect the group globally because of its close connection to the ring Z. Okay, now let's turn to a non-arithmetic case. So in the non-arithmetic case, it's much more mysterious. In general, no one knows how to characterize the matrix entries in a non-tautological way. In other words, we can find generators and can say the matrix entries are the entries in the matrices you get by taking products of generators. I don't consider that a characterization. We can't globally from the outside tell you when something is going to arise. It's even worse to determine which pairs of integers are columns, these integers being integers in a suitable field, and it can be very hard to determine what the cusps are of one of these non-arithmetic groups. Well, here's a corollary of the theorem that I announced at the beginning. In fact, I can tell you what the cross ratios are in a particular case, the first case after the arithmetic case. Arithmetic is when the trace field is Q. When the trace field is quadratic over Q, everything that can be a cusp is. And what that means is that the cusps, basically up to a normalization, coincide with the points of the field, the trace field, KPQ. So if the group has to do with Q adjoin root 5, as it will in an example, then the cusps, when the group is suitably normalized, will just be Q adjoin root 5. And the proof of this theorem, the reason that this can be done is that, in fact, every triangle group is somehow related to one of these geodesic curves on a suitable Hilbert modular variety. Okay, so let's look at the example that is going to occupy us for today. It's what I call the golden Hecka group, the golden being, of course, a reference to the golden ratio, gamma, which is 1 plus square root of 5 over 2. So the golden Hecka group is the Hecka group 2, 5, infinity. And it's just like the group SL2Z, we can say what its generators are very easily. It's generated by translation by the golden ratio and by Z goes to minus 1 over Z. So it's generated by the two matrices I've written down here. And it has a fundamental domain that's very similar to the fundamental domain for SL2Z. It's bounded by two vertical lines and a circular arc. It's just the vertical lines don't go between minus 1 and 1. They go between minus gamma over 2 and gamma over 2. And we can see the action of the generators here. Z goes to Z plus the golden mean, identifies the vertical sides. Z goes to minus 1 over Z, creates this orbifold point of order 2, and it identifies the other two sides of the fundamental domain, gluing it up to become this 2, 5 infinity sphere. And analogous to the 2, 3 infinity triangle we saw for SL2Z, there's this 2, 5 infinity triangle. So this is the golden Hecka group. And a corollary of theorem 2 is that, in fact, we do know what the cusps of this group are. They are just Q adjoin root 5, which is the associated quadratic field, and the point at infinity. And in fact, this was first proved by Leutbecker in the 1970s using an argument that was quite special to this field. And we'll maybe get a glimpse of the spirit of his argument as we go. Then the theorem Q actually applies to infinitely many different groups, and the proof is very uniform and somewhat different in spirit. It's based on this descent argument using a suitable height. So let me tell you what the analog is of the fairy packing. Maybe this is a little bit in the spirit of Dennis's famous lecture that Edson recounted. So you can make an interesting packing. It's not like the hexagonal packing, it's a close relative. Consider this horizontal line at the top as being a circle, and then there's a little necklace of 5 circles. Below it, there's the unit circle sitting on gamma, and then there's another adjacent to that, another adjacent to that. So there's a little 5 tuple of circles here. And now, after you've drawn those 5 circles, you look closer to the real axis, and wherever you have 2 circles meeting, you insert 3 more. And then underneath them, you insert 3 more, and you keep going. And the claim is that first, the bases of all the circles you get belong to the field Q adjoin root 5. And in fact, if you pick any element of that field, it eventually arises as the bottom of one of these circles. That's a geometric version of the theorem on the cusps. Now here's another way to look at the theorem. So we all know about golden fractions, continued fractions over the integers. You take a real number, you find the largest integer less than it, subtract it off. Now it's between 0 and 1. Take the reciprocal, subtract off, etc. It can then be developed as a continued fraction. Well, we can also try to develop numbers in what I call golden continued fractions. And it turns out that if you start with a number in the field Q adjoin root 5, it has a finite golden continued fraction. So what you do is you find a multiple of the golden mean that's close to x. So you write x as a1 gamma, and then you take the reciprocal of what's left over. And then you write that as nearly an integral multiple of the golden mean, then take the reciprocal of what's left over. And the theorem is that as you carry out this process, it will eventually terminate. And in fact, that's equivalent to the statement about cusps. It's that every number in Q adjoin root 5 has a finite golden continued fraction. And this allows me to give you an idea of what this statement about quadratic height bounds means. It turns out that the length of this continued fraction and the maximum of the integers that appear here can be controlled in terms of an invariant called the height of this integer x. And the height is basically x is in Q adjoin root 5, but you can write it down as in terms of integers and the number root 5. And basically, the number of digits that appear in that expression is the height of x. Okay, so the quadratic height bounds tell you how long you have to wait roughly for the continued fraction to terminate. And here's another way of thinking about the theorem, a third way, which is that if you have an element of Q adjoin root 5, you can write it, of course, as a ratio of integers in this field. This happens to be a field, a unique factorization domain. So it has an almost canonical expression as a ratio of integers, but not quite, because this field has a non-trivial unit in it, namely the golden mean. The golden mean has norm 1. You can take any integer, multiply it by a positive or negative power of gamma, and it's still an integer. So among all those different ways of writing x, is there some natural way of writing it as a fraction, a over c? And the claim is there is. In fact, it can always be written in an almost unique way as a ratio of a over c, where a and c occurs as a column of a matrix in the 2, 5 infinity triangle group. So there's a little bit of a connection between columns and ways of writing integers in this ring. And then the quadratic height bounds tell you how complicated these numbers a and c have to be. It turns out that the sum of their heights is bounded by the square of the height of x. And we'll see what this square means geometrically from other perspectives to come. Okay, now, yeah, I should have mentioned, right. So the height, for example, of an ordinary integer is it's the logarithm. It's the number of digits needed to express the result. Okay, so I want to say just one little glimpse of how one should be thinking about this non-arithmetic group. You might say this group is a lattice in SL2R. Don't we understand lattices in SL2R? But in fact, this group should not be thought of as a lattice. And the reason is you can think of this, sorry, I think this should have been an infinity. So this should have been a 5 here. Sorry about that. This 2, 5 infinity triangle group sits in the ring SL2 of O, where O is the ring of integers in Q adjoin root 5. It's Z adjoin the golden ratio. And that group sits as a lattice in the product of 2 copies of SL2R. And this is an arithmetic group. So this is a realm that we understand. And what we've done is we've taken a group we understand and we've passed to a subgroup of infinite index. Now this group, SL2O, if you were to project it to either of these 2 factors here, it would be a dense subgroup of SL2R. Our 2, 5 infinity triangle group has the remarkable property that when you project to one factor, it's so thin that it projects to a lattice in SL2R. So one should really not think of it as a lattice, but rather as a subgroup of infinite index in this bigger group that sits in a product of 2 copies of SL2R. And geometrically, this inclusion of groups underpins an inclusion of a curve into the associated Hilbert modular surface. That's why theorem Q applies here. And I just want to mention that the lattice radically breaks the Galois symmetry that this group SL2O enjoys. It's invariant under Galois conjugation, sending root 5 to minus root 5. But gamma is very much not. If you were to take the Galois conjugate of gamma, you get an indiscrete subgroup of SL2R. And so what's happening, for example, with golden fractions, is this very thin group lets us pick out among the infinitely many possible expressions for x as a ratio of 2 integers, a particular one. They all differ by some power of this unit gamma, and gamma acts like a sieve and picks out a natural canonical ratio to attach to every point in the field.
Is gamma 2, 3 or 2, 5?
Gamma, this as I mentioned, that's a typo. Gamma is 2, 5. This gamma at the top. Okay, so that's a glimpse of the sort of challenge of trying to examine the 2, 5 infinity triangle group. Okay, now I want to change gears and talk about billiards. But to do that, I need a little bit of groundwork in moduli spaces. So let me begin by talking about the moduli space of Riemann surfaces of genus G. So this is a beautiful complex variety. If G is 2 or more, it has dimension 3G minus 3. And it has 1 point for each isomorphism class of Riemann surface of genus G. So it classifies those. Now, the good question is, how can I give you a point in the moduli space of Riemann surfaces of genus 2? Or even genus 1? Well, in genus 1, there's a really nice answer. I can say, here's a complex torus, surface of genus 1. You just take this parallelogram, identify the green sides with themselves, and identify the black sides, and it'll wrap up and form a torus. So I give you a polygon in the plane, plus gluing instructions, and out comes a surface of genus 1. Okay, fine, but how can you specify a Riemann surface of higher genus? Well, you can use the uniformization theorem. But it's not the uniformization theorem that usually bears that title. It's the following statement: every Riemann surface of genus G can be built from a polygon in the same way surfaces of genus 1 can. Namely, you can find some polygon in the plane such that when you glue opposite sides or corresponding sides by translation, it wraps up and gives you your Riemann surface X. So it's a kind of flat realization of X. It just comes from a polygon in the plane, the same way a surface of genus 1 does. Now, this should give you pause because you know very well a surface of genus 2 doesn't admit a flat metric. And what happens is when you do this gluing, there's some cone angle that accrues around the vertices of the polygon. And so there's concentrated negative curvature at finitely many points. Okay, but still, beautiful theorem. Why isn't this routinely taught in every complex analysis class? It's because the realization is not unique. And that's because you're not just giving X, you're giving more information than the Riemann surface X. A better statement would be that if you want to construct a Riemann surface X plus a holomorphic one form on that surface, that is a point not in moduli space, but in the bundle of holomorphic one forms over moduli space, the bundle of pairs consisting of X and omega, you can do so by taking a polygon on the plane, taking the one form dz, and then letting it descend to this quotient by gluing. And since translation preserves dz, you get a well-defined holomorphic one form on the quotient Riemann surface. And conversely, every holomorphic one form of genus G can be presented in this way by a polygon. Okay, now what's interesting about having that additional data of the one form? Well, one thing is that it gives you some dynamics on the Riemann surface. Namely, since the horizontal lines in the plane are preserved by gluing, you get a foliation of X by horizontal lines. They're even oriented. So you can talk about flowing along horizontal lines on X. These are in fact just geodesics for the flat metric induced from the plane. So there's a geodesic flow on this surface with this flat, albeit flat metric, albeit with isolated singularities. So that's something interesting in its own right. A Riemann surface plus a one form becomes a dynamical object. Now, somehow, by divine justice, when there's dynamics on every object in a space, there's often a metadynamics on their moduli space. And here, the metadynamics is the action of our friend SL2R, the linear automorphisms of R2, on the space of holomorphic one forms. And the way this works is very simple. If you have a one form presented with a polygon, you just apply a matrix to that polygon. You get a new polygon on the plane, carry the gluing constructions over, and you get a new Riemann surface plus a new one form. So here I've started with a polygon in the shape of an L. The image under a linear map, it still has the topological shape as an L. The translation gluings can still be carried out, and I get a new Riemann surface plus a new one form from this new polygon. Now, how do the dynamics and the metadynamics interact? Well, linear maps preserve straight lines. So in some sense, the dynamics of geodesics on the new Riemann surface is the same as the dynamics on the old one, except the lines may have been stretched depending on what their slope was. Okay, now here's an amazing thing that very rarely happens, but happens occasionally. The first point is, you might say, well, I have these SL2R orbits in this bundle over moduli space. What do I get if I project them down to moduli space? And it turns out that every SL2 orbit projects to give a map of the upper half plane into moduli space. In fact, this upper half plane map is analytic, and it's even an isometry for the hyperbolic metric on the domain and the Teichmuller metric on the target. So these SO2 orbits project to these objects called complex geodesics, which are much studied in Teichmuller theory. But that's not quite right. The map from the upper half plane to MG might not be injective. So there's a group here that should be studied, namely the stabilizer of your one form in SL2R. And that stabilizer is typically trivial, but it might be a very rich group by accident for some very specially chosen one form. Either way, instead of mapping H directly to MG, you can first take the quotient by this stabilizer, and then that quotient space will map into MG. Okay, now here's the miracle. It might happen that the stabilizer is not just non-trivial, but it's a lattice in SL2R. If that were to somehow happen, then this V here would be an algebraic curve in its own right. And then it turns out F would be an algebraic map of that algebraic curve into moduli space. So we get an algebraic curve in moduli space. And what would be special about this curve is that it's isometrically immersed for the Teichmuller metric on moduli space. So it'd be some kind of extreme curve. And now you would expect that somehow if the metadynamics of this one form, that is if its stabilizer is very rich, that should have some impact on the dynamics per se, in other words, on the geodesics on this surface. And in fact, this is a theorem that combines work of Mazur and Veitch. In the event that SLX omega is a lattice, if the stabilizer is very big, then every geodesic on the corresponding Riemann surface is either periodic or it's uniformly distributed with respect to the area measure coming from this one form. And I'll give a hint about why this is true a little bit later.
There's ambiguity in the English.
Sorry?
Every geodesic is, all of them are periodic or all of them are uniformly distributed?
Every geodesic is either periodic or uniformly distributed.
Oh.
Sorry.
Okay. Each one.
Good point, but not both. So in other words, there's two extremes. One is a geodesic might just close. Then obviously it can't go everywhere. It can't be highly chaotic. If it doesn't close, then it's uniformly distributed. So we get a strict dichotomy. There's nothing in between very chaotic dynamics and completely periodic dynamics.
That's the theorem of that you're.
Sorry, it's a theorem of Mazur and Veitch. Now, I haven't given you an example of a Teichmuller curve yet. And in fact, the examples were discovered not in the setting of Teichmuller theory, but in the study of billiards. So let me turn to the theorem that is actually what was published by Veitch in 1989 that gave the first instance of this combination of the ideas I just mentioned. It's a slight variant of what we just discussed on Riemann surfaces. So one can study the dynamics of billiards in finite-sided polygons in the plane. And what I've drawn here is the regular pentagon and a very long piece of a fairly typical geodesic. And it looks, you know, there's a lot of pattern going on there. It's very rich structure, but it also looks like it's filling the pentagon very evenly. And in fact, this is the theorem that was actually proved by Veitch in 1989. He proved that in the regular pentagon, or indeed in every regular polygon, every billiard trajectory is either periodic or uniformly distributed. So it might come back, the billiard trajectory might come back to where it started, but that's very unlikely. And if not, then it fills the polygon evenly. So let me sketch the proof of this theorem and what it has to do with Riemann surfaces. So the idea, which goes back quite a ways, it's even useful in the case of a square, is that to study a billiard trajectory that hits the side of a polygon and then reflects, that's kind of painful to have to deal with that reflection. What's better is to try to absorb the reflection into the space. So instead of having the trajectory reflect when it hits an edge, just put a new pentagon underneath the original one and let the trajectory go straight through into this new space. And then continue that process. Well, when the blue trajectory goes off the lower edge, we could put a new pentagon there, but it would look exactly like the top pentagon. So rather than having the blue trajectory go into yet another pentagon, we can have it just come back to the top edge of the top pentagon and continue there. So in other words, to study billiards in a pentagon, we can take two pentagons, glue them together, and what we're left with is a combinatorial octagon. There's 8 sides left that haven't been glued. And then we glue opposite edges together, and we get an instance of the construction we were just talking about. We get a Riemann surface, this time of genus 2, from this polygon. And it comes with a one form as well. The one form is telling us what straight lines are. And so it's telling us what the billiard trajectories look like. So from this construction, the pentagon is turned into a Riemann surface of genus 2. It turns out the corresponding one form has a unique 0 with a lot of curvature. It's total angle 6 pi around the unique 0. And then the billiards in P goes over to geodesics on this Riemann surface. And now we can go back and try to invoke Mazur's theorem. If the geodesic flow on this Riemann surface has optimal dynamics, then the billiard flow will also have optimal dynamics. But we're slowly moving away from the pentagon. We've kind of lost sight of the pentagon when we went to this surface of genus 2. We've gotten rid of some of the somewhat arbitrary choices here. These going back here to the pentagon requires sort of cutting the surface open. So we've made a more symmetric object by gluing these edges together, and we can look for hidden symmetries of the pentagon. And the hidden symmetries are the stabilizer of this one form in SL2R. So what are the pentagon's hidden symmetries? They're the stabilizer of this one form, and it turns out to be our friend, the 2-5 infinity triangle group. So in fact, the stabilizer is a lattice, and so Mazur's theorem applies. And as a corollary, the pentagon gives rise to a Kirchmüller curve in MG, and the billiards in the pentagon has optimal dynamics. Okay, so let me try to reveal to you these hidden symmetries. Where are they? Well, what I'm going to do is start with a different polygon that's a close relative of the pentagon. This is what I call the golden L. So it's a symmetric L shape. Both long sides are of length the golden mean. And you can think of it in the following way. You take a golden rectangle, and then you stack another one on top of it. So that's a polygon, and we could take this polygon and glue opposite sides to get a Riemann surface. Well, we get a Riemann surface plus a one form in that way, and that one form, that so-called golden surface, contains in its automorphism group first this symmetry 0, 1, minus 1, 0. What that means is you can rotate the Riemann surface by 90 degrees. That's not so unexpected because this L is symmetric under flipping around the diagonal. So it turns out the Riemann surface admits a 90-degree rotation coming from that symmetry. But what's a little more surprising is this upper triangular matrix with gamma. But what that's coming from is the fact that you can shear this Riemann surface by doing independent shears in these two rectangles. So when you glue the two sides of the orange rectangle together, you get an annulus, and you can do a 360-degree Dane twist in that annulus. It'll send this vertical line to this diagonal line, and that's compatible with the gluing. And then you can do exactly the same kind of twist in the annulus above, and those two things fit together to give a real linear automorphism of the surface, which is the same thing as an element in its stabilizer in SL2R. So this symmetry of the L-shaped table gives rise to a second element that stabilizes it. And now we're done because these two elements generate a lattice, namely our friend, the 2-5 infinity triangle group. So that shows at least that this one form of genus 2 has a lattice stabilizer. And in fact, it comes from the 2-5 infinity triangle group. Now remember, what we're going to get at the end of the day is a map of the quotient of the upper half plane into moduli space. And so every point in the upper half plane will correspond to a Riemann surface of genus 2. In fact, a Riemann surface of genus 2 plus a 1 form. And what do we get? Well, at the 2 point of the 2-5 infinity triangle group, the group thing we just constructed, that goes to this golden surface. But there's also this 5 point here. That's a point which is fixed by an order 5 rotation. Well, there's only one Riemann surface of genus 2 that has a symmetry of order 5. It's the one that we just built using the regular pentagon. So in fact, the 5 point corresponds to the regular pentagon. And that shows that the regular pentagon lies on this Teichmuller curve, and therefore it also has at least a conjugate of the 2-5 infinity triangle group as it's stabilizing. So it also generates a Teichmuller curve. It also satisfies this theorem of Mazur and Veitch. So that's how the 2-5 infinity triangle group is related to the pentagon. It sort of encapsulates some hidden symmetries for its billiard dynamics. Okay, now you might want to know what the proof is of the theorem of Mazur and Veitch. And I'm in the middle of a conference on renormalization. How can I not mention renormalization? So I think I'll just say the proof is by renormalization. But you can see renormalization happening 3 different times at once in this picture. First, the group SLX omega acts on the 1 form X omega. It acts on a surface of genus 2, preserving geodesics, not sending them to themselves, but sending any family of parallel geodesics to a new family of parallel geodesics. So this can be used to renormalize the geodesic flow on the corresponding Riemann surface of genus 2 that's built from the pentagon and its reflection. The second way the renormalization group acts, it's quite closely related to one, is via the Teichmuller geodesic flow. This is the action of the diagonal subgroup of SL2R. And what that diagonal group does is the following. It takes a Riemann surface foliated by horizontal geodesics, and it shrinks the horizontal geodesics at the cost of expanding the vertical geodesics. So suppose you wanted to study the horizontal geodesic flow, you wanted to show these geodesics are uniformly distributed. Well, a commonly used technique, which is basically what renormalization is about, would be to accelerate the dynamics. Let's make it go faster so that we can see more clearly what happens over a long period of time. And that's what the Teichmuller geodesic flow does, is it accelerates the horizontal geodesic flow. And then the third way we see renormalization happening is by going back to the 2-5 infinity triangle group itself. So remember, this group is generated by inversion and by translation by gamma. So if you're interested in billiards, you could say, I'm trying to understand a billiard path with slope S. Well, I can renormalize that path by taking its reciprocal. And it turns out that doesn't change the dynamics in any essential way. And moreover, I can then subtract off a multiple of the golden mean to make the new slope rather small. S might have been very close to 0. And this is the golden fraction transformation. You take a small number, you take its reciprocal, it becomes big, then you translate by a multiple of the golden mean to make it small again. And understanding how a slope evolves under this continued fraction transformation is another way to apply renormalization and obtain this proof of optimal dynamics. Okay, so I didn't tell you the proof, but I told you different ways that renormalization enters the proof. Okay, so we have this great picture of the pentagon. It has these trajectories. They're mostly uniformly distributed, beautiful. What else could we ask? Well, actually, it's not true that every trajectory is uniformly distributed. Some are periodic. So we could ask some simple questions. They might seem a little peripheral at first. The first question would be, by the way, what are the periodic trajectories? And tell me, for example, what their slopes are. And then, by the way, once you know the slope, can you tell me how long the trajectory is. And I can remember like it was yesterday when I first started doing some experiments in the regular pentagon, not knowing the answers to any of these questions. So here's an experiment that you can try at home. First, you try to find one periodic trajectory in the regular pentagon. Well, here's an obvious one. There's this inscribed star, which joins the midpoint of the bottom edge to the midpoint of the edge that's two over from it. And that's obviously a periodic trajectory just by symmetry. So there's some slope S, and the combinatorial length of that slope is 5. It hits the sides of the pentagon 5 times. So just as an attempt, just as a guess, I'm going to try multiplying that slope by an integer and see if that happens to preserve periodicity. That does work, by the way, in a square. If you take a periodic slope and multiply it by an integer, it's still periodic. So I multiplied by 4 and I got a new periodic trajectory, but look how complicated it is. It hits the size 469 times, and it's pretty dense in the triangle. And that was just multiplying by 4. What if I multiplied by another small integer like 20? Well, here's the picture of a billiard path with slope 20s. It hits the sides more than 2,000 times, and the picture looks completely dense. And now you try 30, 40, 1,000, maybe some number around 6,000, and the picture is always the same. It's black. But after a very short amount of time, the computer stops working. So in fact, if you were to take the slope 6765 times s, its length can be computed exactly, and it hits the sides of the pentagon about 10 to the 25 times. So you're not going to discover that that trajectory is periodic. And so as you're doing these experiments, you start generating periodic trajectories and you think they're all periodic, but they're getting so long, you can't ratify periodicity by computer. The lengths very quickly become enormous. That's an interesting phenomenon in its own right. So here's the theorem. In fact, the periodic slopes are simply all multiples of s, not just by integers, but by any rational number, in fact, by any element of the field q adjoin root 5. Now, you might say, okay, and then how long are they? How many times do they hit the sides of s? And the answer is the log of the number of times a trajectory hits the sides of the pentagon is bounded by the height of the slope squared. And that's what we're seeing in this previous picture. The lengths grow like the square of the complexity of the slope. So for example, if you were to multiply s by 10 to the n, the length of the trajectory would be like 10 to the n squared. So if it becomes enormous much, much more rapidly than the complexity of the slope. And so you really need a theorem to ratify this periodicity. In fact, this exponent 2 is sharp. Anyway, what's the proof? Well, the proof is, we've already seen it. It's that the periodic slopes, it turns out, it's easy to see, they correspond to the cusps of our group SLX omega, which is the 2, 5 infinity triangle group. And theorem Q tells us what those cusps are. They're Q adjoin root 5. That's why we know what the periodic slopes are. And moreover, the golden fractions A over C describe for a given slope how it unfolds to give a long vector in the plane that if you have a periodic trajectory, you can just sort of unfold all of the consecutive steps it takes. You get a very long vector in the direction of the given slope. And that vector is exactly this vector AC that comes from one of the columns of the matrix 2, 5 infinity. So the main point is that the results on billiards also follow from theorem Q. Okay, so let me move on to another topic. I'll skip a last comment here and say just that although I concentrated on the regular pentagon, there's many families now known of polygons that have optimal billiards. So for example, this L-shaped table using 1 and gamma, you can replace gamma with infinitely many other quadratic integers here in infinitely many other fields. And you also get optimal dynamics. And there was a new family discovered just a couple of years ago in my joint work with Alex Wright and Ronen Mukamal. And it turns out that there's these arrowheads where you can also vary the length of one of the sides of the polygons. And these also have optimal dynamics, and they obey all of these height bounds and so on that we've been discussing. And in fact, although there's some chance there are more billiards yet to be discovered, there's now about 4 or 5 families known. It took 40 years to find them. We now know that they will all fall within the reach of theorem Q, because they will all be associated to quadratic fields. And this is a rather deep theorem of Eskin, Philippe, and Wright, that in each genus, almost all the interesting Teichmuller curves come from real quadratic fields. There's at most finitely many that come from cubic fields or fields of higher degree over Q. Okay, so the connection to quadratic fields is not accidental. So let me finish by going back to the discussion of the 2-5 infinity triangle group and billiards, and tell you one additional fact about them that can be gleaned and that is inspired by this connection with dynamics and by the picture of the involvement with bundles over moduli space. So let me first talk about measures. So we have this theorem that every trajectory is periodic or uniformly distributed. Okay, so how are the long periodic trajectories distributed? So you might think, well, an aperiodic trajectory is uniformly distributed, so the longer a trajectory becomes, the more nearly uniformly distributed it should become. And that's in fact true, for example, in a square table. Well, Davis and Liliev showed no, in the Pentagon, long trajectories do not have to be always uniformly distributed. In fact, they gave this extraordinary example of a family of trajectories in the Pentagon that's arbitrarily long, and yet they all avoid this little circle in the center of the Pentagon. So they're not uniformly distributed at all. And this example, I think, was discovered in a really remarkable way. Diana Davis proved in her thesis a theorem describing all of the periodic trajectories combinatorially. And they have very different appearances. And then she started making wooden models of these trajectories. That is, she'd build a wooden pentagon, and then she'd have a computer printer burn on it the track of one of these trajectories. And some of them were very beautiful. And then she started selling them as earrings. And she wanted to give the customers a choice of patterns. So she drew the first 500 periodic trajectories, and some of them had these holes in them. And so this was first discovered empirically by just looking at all the trajectories. And so there's this big problem. Periodic trajectories are not always uniformly distributed. So you can ask, what does the space of measures look like that come from these periodic trajectories in the limit? Do you, for example, get a Cantor set of measures by taking trajectories whose slopes are tending to 0? If you look at all the possible limiting behaviors, would you get a Cantor set of measures? And they found a sort of tree-like structure to the space of periodic trajectories, which suggested you might get a Cantor set of measures. Well, here's the solution to their question. In fact, for each periodic slope, if you look at the measures you get from trajectories that converge to that periodic slope, those limit measures form a countable set, not a Cantor set, a countable closed set that's homeomorphic to omega to the omega plus 1. And these measures describe the scarring behavior, as it's called in the theory of billiards, the failure of trajectories to equidistribute, how they do distribute when they don't distribute evenly. And they also allow us to describe the closure of all of the ergodic measures for the geodesic flow. The closure consists of sort of uniform measure coming from every direction, plus these countable sets, the countable closed sets that you have to add in a sort of blown up fashion for every periodic direction. So we now know what the closure of the ergodic measures are. They're not all ergodic, but they blow up in terms of these countable sets. More to the point, you might have wanted to get uniformly distributed trajectories. And in fact, quite frequently you do. When do you get uniformly distributed trajectories? The answer is you get uniform distribution from a series of periodic slopes if and only if the lengths of their golden continued fractions tend to infinity. Remember, every slope in the field has a finite golden continued fraction. If that continued fraction gets longer and longer, then uniform distribution is obtained. So we understand now really what the obstruction is to uniform distribution and why it occurs. So let me finish by just giving you a glimpse of the answer to this question and then a little hint about what we don't know, what the frontier is. So first, let's go back to matrices. I mentioned that when you have a non-arithmetic group like 2, 5, infinity, no one knows how to succinctly describe what numbers occur as matrix entries. Well, here's a result towards limiting what those matrix entries can look like. So let M be the set of all non-zero matrix entries. These are going to be integers in our field. And for each one, we can look at the ratio of M and its Galois conjugate, M prime over M. I call that delta of M. And then the theorem is that if you rescale delta of M, you get a set whose closure is contained in -1, 1. It's homeomorphic to this complicated countable set, omega to the omega plus 1. And remarkably, it's a semigroup. So there's some sort of hidden multiplicative structure in the matrix entries of these non-arithmetic groups. And there's also a rather subtle topological structure. To be a matrix entry, the ratio M prime over M is highly constrained. It has to land in this countable closed semigroup. Whereas the matrix entries in SL2O would give you a dense subgroup of R.
What is M prime?
M prime is its Galois conjugate. So M is in Q adjoining root 5, and N prime is you send root 5 to minus root 5. It turns out M prime is always smaller than M. Okay, so here's a picture. Oh yeah, sorry. Before I do that, I just want to say this ordinal omega to the omega, this is a countable set with the property that it has limits, and then its limits have limits, and its limits have limits of limits, and so on and so on. But when you intersect all of those, you're left with nothing. And it appears in many other places in mathematics. The set of Pizot numbers are homeomorphic to omega. The set of 3D hyperbolic volumes is homeomorphic to omega to the omega. There's something called the Weyl spectrum that's also homeomorphic to this ordinal. And it's nice to be able to add this shadow of a non-arithmetic group to the list. So here's a picture. One can actually draw a picture of this set M prime over M as M ranges over the matrix entries. So there's a lot of dots in this picture, maybe 50,000. If you project them to the real axis here, to the horizontal axis, you get the set I'm talking about, this closed countable set. And you can see there's an accumulation point at gamma to the -4, another accumulation point there visible as spikes. And then these spikes accumulate, and that gives you an element of the derived set of the derived set. And this limiting process iterates again and again and again. So there's limits of limits of limits. And then the superaccumulation point is just the origin here. And if we go back to the measures on the pentagon, something similar happens. We have accumulation points of measures and then multiple accumulation points. But as the continued fraction goes to infinity, you get accumulation points that are closer and closer to the uniform measure. It's sort of the ultimate accumulation point of this countable set. Okay, so I'm slightly over time. Let me just finish by looking beyond 5. So the hexagon is pretty simple, but the heptagon, the regular 7-sided figure, has billiards that I don't understand at all. So let me just give you a hint about what's known, what's not known. So let's discuss billiards in the regular 7-gon. Well, again, we can find a periodic trajectory pretty simply. Let's say it has slope s. But now the field we're working in is cubic over the rational numbers. My theorem Q was for quadratic, doesn't apply. We can ask which slopes are periodic, and the answer is we don't know. The slopes basically lie in this field. And if we take this particular slope S, we see a trajectory of length 7. If we double it, we see a trajectory of length 2000 or so. It's very dense. If you multiply it by other numbers, we don't know if it's periodic or not. We also don't know how to test if it's periodic, because how long should we have to wait to determine whether or not the trajectory is going to close? So this is actually just changing 5 to 7 brings us well past the reach of the theory that's currently been developed. And but I do want to throw out just a mind-blowing conjecture. This has been kind of a secret for a while because many people were working on it, but nobody's been able to prove it. So I think I can announce it. And it's perfect for a conference on renormalization. So here's the blind, wild conjecture. If you have an element of this cubic field, it's either the fixed point of a parabolic element in the 2, 7 infinity triangle group, in which case it corresponds to a periodic slope, or it's the fixed point of a hyperbolic element. So in fact, every element in the field is fixed by some element in this group. We're nowhere close to proving that, but here's a way to say it. It's either only finitely many times renormalizable. That's the parabolic case. You try to develop its continued fraction, and it just stops after some finite number of steps. That's great. Then we understand what's going on. Or it's infinitely renormalizable, in which case it sort of corresponds to a pseudo-Anosov element on the surface of genus 3. And also there's a complete unfolding of information about it. And so the bold conjecture is that although we don't know the periodic slopes, the slopes that are not periodic should be infinitely renormalizable. So I'll end with that challenge and a picture of a couple of the periodic slopes in the heptagon. Okay, thank you and happy birthday, Dennis.
Thank you. So, Kurt, so on the torus, so when all of us know that there is a rich theory of nonlinear flows based on continued fraction expansions, Km, Riemann, cos, this great stuff. And now you have your pentagon surface. You may consider nonlinear flows on this pentagon surface, which are topologically equivalent to the flows you took a look at. And do you think that there could be a similar theory developed on this golden continued fraction expansions? So for nonlinear flows, is a
That's a great idea. So I think I saw Giovanni Forni here. I also see Karina is in the audience. They are much better equipped to answer that than I am. And given the informal nature, any of you guys want to weigh in?
Giovanni, are you here?
Yeah, I'm here. I think Yeah, there is. Well, one big difference is that there will be abstractions to whatever you want to do. So it's not like the rotation number determines everything. To be, you know,
Just finitely many of
simple. But
yeah.
there are results by Selim Ghazouani in that direction, and also by Marmi Musayokos before Selim.
Well,
I think that's what you're.
if it talk on that yesterday, but somehow here it is very specific. There is this continued fraction expansion, kind of the Gauss transformation is there, and maybe everything can be made very specifically brought to the level of Arnold-Terman-Yakos.
Well, I mean, it's not a global theory. I mean, the global theory is, for now, is I don't think anybody has any idea how to develop it. So Terman-Yakos is a global theory. This is just a local theory for small perturbations. But the KM approach has not been worked out, so you have to use renormalization.
Do you think that there is a chance for a global theory? Because the normalization is there. Just little thing left.
Marmi Musayokos in their paper have conjectures about what could be true, but I don't. I think the person probably you could ask the question is Selim.
Selim is here. Selim? No.
No, I don't think there is Selim, but we do have a result which is in some sense in the global direction. This is what Selim was talking about yesterday in Genus 2, and it's based on, yeah, it uses some result on Marmi Musayokos on wandering intervals. So actually, no, I think it's a good point to try to look at the Vich case as a, yeah, no, no, I don't know, but yeah. So actually, can you repeat one more time what you were suggesting? So, as a question, yeah.
Just suggesting to build up somehow theory for nonlinear flows of these pentagon surfaces that Kurt was talking about, based on the golden continued fractions. It is somehow, well, it's certainly related to Rousey induction, but maybe it is a better way of presenting things, and maybe it would give some better control of golden Gauss map.
No, I understand, but
we don't know whether it's topologically conjugate.
Assume we can assume that topological. We can start with that as topological conjugacy, and then
I think this is the, if I can intervene, I mean, I think the approach to start with topological conjugacy hasn't worked out yet. I mean, there are no results like that. There's a conjecture by Marmi Musayokos that says basically that if you have C0 conjugacy, then you have C1 conjugacy.
But Giovanni, but you don't know the latest thing that we were doing with Selim is indeed proving the special case of this conjecture. So we have this dynamical dichotomy about renormalization for general IT that you basically can show that either renormalization is recurrent, and recurrent in a good way, in which you can kind of prove some a priori bounds and some convergence of renormalization, or you diverge, and if you diverge, you can prove actually you can reduce the existence of wandering interval to that one of the affine case. So we cannot complete the picture in either, we can only do it in Genus 2 because Marmi Musayokos shows us that if you have a second Lyapunov exponent, if your affine IT projector, the log slope is in the second Lyapunov exponent, then you have wandering intervals. So yeah, so to complete the picture, one should have to generalize Marmi Musayokos to other to the whole unstable space. But modulo that, we have some case of global rigidity. Okay, you have to assume also that the boundary is 0, because otherwise there really are counterexamples. If you have, you can have, okay.
So when you say, so you mean for not just for small perturbation, but more generally for anything?
Yeah, it's not a local result. It's kind of about global dynamics that so.
Yeah. I mean, in this special billiard system you consider, can you say something interesting about spectral properties? If you consider Laplace operator in these domains and
Actually, another curiosity is whether anybody has looked at quantum chaos. But it has been looked at least from by
I've done a bit.
physicists.
But
It's
in,
starting.
in engineering, you have some maps which were on lozenges, where you take your lozenge, you turn it from one position to the next one, and what comes out you bring back. And there, so this depends on an angle. For most angles, you don't know anything. It seems that there is density for positive measure of the parameters. And the only examples which are understood using renormalization. We did some with Adler, Roy Adler, and Bruce Kitchens, but and then some other examples were done by Vivaldi and Lowenstein. But most cases are not known at all, and this really resembles a bit what was told here, except that the understanding is even lower in this other case, which is an engineering case. And there are some other engineering cases which have, where renormalization seems to be the natural tool to work with.
Kurt, Kostya has a question to you.
Yeah, I already asked it, but I think you didn't hear me. I asked about spectral properties, if you consider Laplacian and these domains, whether they're.
No, thanks. Great question. I heard you. I was waiting for somebody in the audience to answer. No, that's been an idea. I mean, that idea resurfaces periodically in the theory of flat surfaces. It would be very interesting to study the Laplacian on this flat metric, and as well as the eigenfunctions. Do the high energy eigenfunctions equidistribute like they should on a hyperbolic surface? I don't know of any results in this direction, but maybe there are others who are more recently informed here. I just know the question. So let me just throw out another comment that I learned from Dennis, although I think the comment is due to Gromov. If Gromov were to look at what I'm doing, he might say, you're like the kid who's lost his toy and he's out looking for it in the yard. And the parent says, well, why don't you look for it in the closet? And the kid says, but it's dark in the closet.
The best version of it I have heard.
So, Kurt, another question. Do I understand correctly that the analogs of this golden Gauss map exist for all quadratic algebraic numbers because of periodicity of continued fractions? Or
No. I mean, there's a good theory of continued fractions only when the corresponding, there's a good theory of continued fractions for each triangle group of signature 2q infinity.
Mm-hmm.
And so when q is 3, you get the ordinary continued fractions. When q is 5, you get the golden continued fractions. When q is 7, you get some kind of continued fractions over a cubic field. When q is 8, you get continued fractions in q adjoint root 2. And that's basically it. There's only a few examples where you get quadratic fields and then the degree goes to infinity. But you can't start with an arbitrary, I mean, there's not a good theory of continued fractions for an arbitrary quadratic integer, because there's not the two transformations, z goes to 1 over z and z goes to z plus that integer, usually don't generate a lattice.
Maybe one should speak more in terms of renormalization and less in terms of continued fraction, which would then emerge when you recognize them. But the general concept behind that might be more renormalization than.
Hi, Kurt. This is Chris Bishop.
Yes, hi. Good to see you.
I wanted to thank you. I learned something really important from your talk. That's a seven-sided figure. It's called a heptagon. I thought it was a septagon. It's a term I'm using in one of my current preprints, but I Googled it and I discovered that heptagon is preferred to linguistic purists because it combines two Greek roots and doesn't combine a Latin root with a Greek root. And so I'm going to have to go back and change my paper.
Or you could change it to zebenagon.
Yeah. The other thing I was going to ask about was, I mean, one thing I've been thinking about recently is decompositions like triangulations of polygons, or cutting a polygon up into simpler shapes. And one thing you can do, of course, with the planar polygons, if you had two different ones that share the same edge, you could glue them together with that edge and then keep all the other identifications together. And I was wondering if there's ever any situations in which the billiards on the combined thing can somehow be deduced from the billiards on the pieces. It doesn't seem like that would work out very well because the Riemann surfaces don't seem like they would be related, but does it ever help to do that?
Yeah, to the contrary, it's extremely helpful. So before the work of Eskin and Mirzakhani, which settled this issue in general, there was a big open problem, which was, does the dynamics of SL2R on the space of holomorphic one forms obey some sort of rigidity analogous to what Ratner's theorems predicts for the action of SL2R in homogeneous spaces? And I proved that in the case of genus 2. And the proof uses the following fact. If you have a one form of genus 2, you can always obtain it from two genus 1 one forms by taking two tori, slitting them open along slits of equal length, and then gluing them together along the slit.
Okay.
In fact, every form can be presented in that way in infinitely many different ways. And if you've glued them along this slit, then the dynamics looks pretty complicated because geodesics can cross the slit, go over to the other torus, run around, come back again.
Yes.
But what's perfectly understood is dynamics parallel to the slit, because then there's no
Okay.
between the two sides. And it's by exploiting this sort of image of SL2R cross SL2R, or of the space of one forms of genus 1 cross itself in the space of two forms, that it was possible to deduce Ratner's
There's
theorem.
exactly one direction in which the decomposition sort of simplifies things and everything else.
That's right. That's right.
So are there any sort of interesting open questions about which polygons can be decomposed into what simpler kinds of shapes that would be useful? I mean, like, is it helpful to know that you can take polygons at certain angles and decompose them into certain pentagons or triangles?
Let me throw out this, Chris, which is, you might say, this is not quite an answer to your question, but it's, you notice that I tried to get rid of the polygon as fast as possible.
Yes.
I glued it together, but you might say, tell me really, how does the Pentagon know about these internal symmetries? And the way it knows about them is by scissors congruence.
Yes.
Every element of this group, what it is actually telling you a way to take the Pentagon, cut it into many different pieces, apply SL2R to all of those pieces, reassemble, and get the regular Pentagon again.
That's interesting. The paper where I was using the word Heptagon also contains the word scissor congruence in it as well. So that's interesting.
Yeah, great question. There's so much to understand about polygons.
What is this SL2R equivalence? What is the set of equivalence classes under SL2R scissors congruence?
So there's this action of SL2R on the space of holomorphic one forms. And its orbits are, the combination can be thought of as what you get from polygons by combining scissors congruence with the action of SL2R. Two scissors congruent polygons give the same one form, and two SL2R equivalent polygons gives points in the same SL2R orbit.
Repeat the last two sentences again.
Yeah, so there's something that I've hidden the polygon by talking about the space of holomorphic one forms, and let me just say again what the action of SL2R is there. If you have a one form on a Riemann surface, you can just multiply it by a complex number of modulus 1 and rotate it. That's a circle action. The second thing you can do is you can use the foliations it defines to create a Teichmuller geodesic. That gives an action of the diagonal group. You put those together, you get an action of SL2R on the space of one forms.
Yes.
What are the orbits of that action from a naive perspective? Well, you think of a one form as being given by a polygon. But two polygons give the same one form if you can cut them up into pieces, slide the pieces by translation, and reassemble. So call that maybe special scissors congruence, because I'm not rotating.
Translating, yeah.
They're on different surfaces.
Sorry?
What does it mean to be the same? Because they're on different surfaces now.
It means that, so if you take a polygon and glue sides, you get a Riemann surface plus a 1 form. You have 2 polygons and you glue sides. If you get the same Riemann surface up to isomorphism.
Oh, up to isomorphism. Okay.
Yeah.
Then.
And so the naive way of saying.
That classifies the 1 forms, the scissors congruence plus SL2R. And then you said something about the orbits.
Yeah, no, just scissors congruence is the same. So polygons up to scissors congruence, assuming you only translate the pieces, is the same as the space of 1.
Yes.
And then you could throw in the action of SL2R, which you can also see at the level of polygons.
Yes.
And so if you take polygons up to scissors congruence plus SL2R, you get the same thing as the SL2R equivalence relation on 1 forms.
So any 2 polygons of the same area are scissors congruent, but not with just translations.
Not with just translations.
So
exactly.
it's sort of an interesting difference there.
Yeah,
So,
no, it's a very profound refinement to not allow rotations.
that's fascinating.
In your
After your
chapter,
first slide, I was worried I wasn't going to like your talk at all, but then it got better and better and better as it went on. So
And finally, the heptagon. So,
yeah, so we
well,
got all the way to linguistics.
I will look later for your rating. I hope it's at least a thumbs up.
Okay.
in your talk, the sets of points on of the real line where the cusp touches the real line is a field. It's a quadratic field, in fact.
In the case of these special triangle groups, like the
Of
2
the special triangle.
right, it happens.
So I guess it's not a general fact. So when it is a field, are these fields classified?
So it's that's a good question. So I told you that when you have a quadratic underlying field, then the cusps are the field. Everyone believes that when the triangle group is defined over a cubic or a quartic, any field of height degree 2 or more, greater than 2, that the cusps are not the whole field. But the proof of that, obvious breakdown of the theorem that holds for quadratic fields, has only been carried out in a sort of case-by-case basis. I would say it can only happen when it's a quadratic field, but that hasn't been proved. It's probably much easier to prove than the classification of what the cusps are in that case, just to show that they're not as big as you think they could be.
I ask you a question which is maybe a little bit silly, but you know, when you have the picture for the ferry packing, right? You have these, you have the rationals as the set of tangencies, and at each rational, if you have a rational P over Q in a reducible form, then the diameter of the circle that touches it is like 1 over Q squared. Is there something similar for the Q square root of 5?
That's not the least bit silly. Thank you, Edson, and good to see you.
Nice to see you too. Yeah, of course.
Good to see you, brother Edson. So look, luckily I have a blackboard here. So you're right, over in SL2R, the ferry circle that rests on the point P over Q, the height of this circle is exactly 1 over Q squared. And that has to do with the fact that the matrix PQRS is in SL2Z. Provided P and Q are relatively prime, you can choose R and S, so this has determinant 1. And then you just apply that matrix to this horocycle, the one that is a neighborhood of infinity. It says infinity here, and the diameter of what you get is height 1 over Q squared. So what happens for the golden triangle group is that this guy rests on a point of our field, and there's many ways to write that point as a ratio of integers in our field.
Mm-hmm.
There's only one way, though, that's a golden fraction. And so you have to write it as a golden fraction, and then the height is 1 over C squared.
Ah, that's nice. Yeah.
Okay. And now what happens is that this point might be 6257, something like this, it turns out that these numbers are like 10 to the 25 over 10 to the 25. And so this diameter here is 10 to the minus 25. So it's amazing that those horocycles are even there, and they're invisible in the picture.
Oh, that's nice. Oh, thank you. Yeah.
Good question.
Okay, thank you.
So what is the, oh, go ahead, Michael.
Yeah, I was maybe this is, doesn't fit now, but it was this eigenvalue distributions. I wonder if people in Fourier integral operators like Hermander and Deusermatt and those people, they might have done something in that direction, but I don't know this very well. Well, it was just.
No, it's a good comment. I hear this idea resurfacing, and like many of you, I haven't been to a conference in person in quite some time. The online conferences are great, but I haven't heard more about this topic lately, but a lot of people have mentioned it in the past.
It's pretty old. It's pretty old what I was referring to. I guess it's sort of 80s or something.
That's good to know that exists.
Yeah.
So what do you think makes this quadratic field special for this cusp picture?
It has to do with the fact that 2 is 1 plus 1. So what happens is in the middle of the argument, there's some height discussion, and what's happening is there's a term that's going to minus infinity exponentially fast, going to 0 exponentially fast. It's like e to the minus t. Then there's another term that's growing, and it might grow as fast as e to the t, but in fact, it grows more like e to the ht, where h is less than 1. And so the e to the minus t always beats the e to the ht. Now in a cubic field, the competitors are e to the h1t times e to the h2t, and both h1 and h2 are less than 1, but their sum could be bigger than 1. That's it. And you might say, well, maybe there's some magical reason the competition is still 1, but it's not, because we know there are these cases defined over cubic fields where you don't get every point as a cusp that you'd like to. So we don't understand that yet. So you can think of it in terms of continued fractions. Somehow, in the case of a quadratic field, there's a way to prove the continued fraction terminates. So somehow each step of the Gauss algorithm makes the number simpler. And there's various, well, this is how Leutbecker's proof worked, is he proved that the continued fraction operation simplifies somehow, some number goes down. My proof works by using the flow instead of the number and showing some much more canonical quantity goes down. And that makes it much easier and more uniform. But what's happening for the heptagon is somehow the continued fraction is trying to get smaller each time, but it doesn't always finish. But when it doesn't finish, it becomes periodic. So somehow it gets into a bounded regime, and then it's stuck in that bounded regime, and so that forces periodicity. So I mean, one can imagine a mechanism that's leading to what we're seeing for the heptagon, but no one knows how to show that that's what's actually happening.
Why the name theorem Q?
Sorry?
Why the name theorem Q?
Q for quadratic, and also because I'm jealous of Mike Friedman's station Q in Santa Barbara.
Any more questions, comments, stories?
I have just one thing I want to say, which is not, again, congratulations to Dennis, and I want to thank you, Misha, and the other organizers for putting together this amazing conference and for letting me talk to such a great audience. It's wonderful to see so many friends here, if only briefly. Thanks.
Thanks so much for coming, Kurt.
Yeah, my pleasure.